Telescopes keep getting stronger, and the assumption is simple. The more we see, the more the universe should make sense. In 1998, astronomers focused on distant supernovae, using them like markers spread across deep space. They expected a clear pattern, showing gravity slowing the expansion of the universe. On their screens, the data begins to form a curve that should bend one way. It bends the other. Instead of slowing down, the expansion appears to be speeding up. The light from those exploding stars arrives slightly stretched, as if the space it traveled through is growing faster than predicted. That shift changes what is happening between galaxies. Distances are not just increasing, they are increasing faster over time, pulling far regions of space out of reach for future observation. The assumption that better instruments always reveal more starts to weaken. If expansion is accelerating, what exactly disappears from view? Astronomers keep turning to deeper sky surveys, watching distant galaxies shift across their maps as if the universe is slowly drawing a line they cannot cross. Telescopes still collect incoming light, but some regions begin to thin out, with fewer new signals arriving from the same directions. Repeated scans return the same frozen result. No new light arrives to update what is already on the screen. In some directions, the sky updates normally. In others, the feed simply stops changing, as if the region has fallen out of sync with observation. As expansion continues, a boundary forms where light emitted from far galaxies no longer has a path that reaches observers. On telescope screens, galaxies that once updated regularly stop changing, then fade from new data entirely. The visual effect is not sudden disappearance, but gradual silence in specific regions of space, where instruments still point but receive nothing new. The problem is no longer how strong the instruments are. The problem is that nothing new is arriving from certain directions at all. What seemed like a temporary visibility issue becomes permanent removal from what can be studied. If entire regions of the universe can fall out of reach in this way, what kind of knowledge is being lost at the same time? The gap grows without warning. Across these independent observations, a consistent picture keeps forming. Measurements tied to distant supernovae, the overall expansion rate, and the large-scale distribution of galaxies all appear to reinforce each other instead of contradicting one another. Each method is built differently, yet they converge on the same outline of how the universe behaves. That convergence makes the result feel anchored, as if multiple instruments are independently locking onto the same underlying structure. With that alignment in place, the conclusion feels increasingly secure. It becomes reasonable to assume that the essential story of the universe has already been assembled in its core form and can be passed forward without losing its meaning. Even if some regions become harder to see over time, the broader framework still appears intact. Future observers, working with fewer visible galaxies, would still be expected to recover the same underlying structure of reality that is visible now. If that confidence holds, the question quietly shifts. If the story is already stable, why would any missing galaxies matter at all? Arrays of telescopes continue scanning deep sky maps, while teams compare incoming data against older records. The same large-scale structures still appear across different instruments, reinforcing a consistent picture. But as the scans extend farther out, they begin depending more on the most distant signals, the ones arriving more weakly over time. Some regions still refresh normally on the screen, while others begin to update less often, as if the incoming light is starting to thin out before it ever reaches the instruments. As this continues, measurements built from galaxy distributions, expansion tracking, and distant light sources still agree when placed side by side. On monitoring screens, Every dataset aligns cleanly, with no obvious contradiction between methods. Yet the regions feeding those measurements are slowly thinning, so fewer fresh signals arrive to adjust or challenge the maps being built. Even with fewer inputs, overlapping datasets continue reinforcing each other. Maps still layer neatly, and large-scale structures appear stable when compared across instruments. But the shrinking range of accessible galaxies leaves fewer independent sources to test those patterns. What looks like a complete reconstruction persists, even though parts of the observational record are no longer being refreshed. That stability makes it seem reasonable that future observers, working with reduced visible galaxies, could still reconstruct the same cosmic structure from what remains. On their instruments, surviving signals would still form coherent patterns and support consistent measurements. From that perspective, analysis would continue without visible breakdown, even if it relied on a narrower slice of the sky. The question that remains is what those same measurements would imply when the missing parts are no longer part of the comparison. Monitoring centers continue to cross-check incoming cosmic surveys, layering fresh measurements over older maps as they arrive from different instruments. As these streams are compared, the same underlying patterns keep appearing, even when traced through separate methods built on different assumptions. Yet some of the signals those methods rely on are slowly thinning, as the most distant galaxies drift beyond reach and stop contributing new light to the record. Because of this, several key observations that support the current picture of the universe increasingly depend on structures that are becoming less accessible over time. What remains still aligns cleanly, giving the impression of a complete and stable story. From within that stable picture, it is easy to assume the full history is already secured, ready to be inherited without loss. But the same system that preserves consistency also filters what can no longer be seen. If that holds, a strange possibility emerges. A civilization could perform correct science using what is available, while missing the parts that once made the story whole.